Alright, I'm going to start you guys off on this discussion right here. And I'm going to leave a little bit of this for you to fill in without me. Alright. It says that a graph is symmetrical if I can take any point, x, y, and if I take the opposite of those points, x and y, the x value and y value is still on the graph. And so with this graph, we know we have a few points. For instance, 1, 1's on the point. The question is, can I take the opposite of those, -1, -1, and have it still be on the point graph? Well, it sure is. Down here is -1, -1. I think you'll find out that all of those points, for instance, 2, 8, the opposite of 2, and the opposite of 8 is also on the graph. This is really right here the definition of what an odd function is going to be. And in this case, is it symmetric about the origin? We're going to say yes, because every set of ordered pairs, when I take the opposite of both the x and the y, it's still on the graph. So we know that a cubic function is symmetric about the origin. Now, recall what these guys mean. This would be the opposite of my out. This would be a change in A. Remember, that's a reflect over x, and this is change in your B value, which is to reflect over the y-axis. If I was to reflect over the x and I was to reflect the other function over the y, what would you notice? So I want you to graph it, but you don't really need to graph it. You can kind of see what would happen if you did this reflection and then this reflection. All right. If you have a graphing calculator, feel free to go ahead and put that in your graphing calculator, but I still want you to write what you notice. All right. So now we're going to go back to A, B, H, and K. I'm sure you're going to get very familiar with these. A, B, H, and K. And we're going to graph these by hand. So I'm going to come over here, and I'm going to figure out how this guy moves, and that'll be my first point that I plot. This guy right here is 1 right. This guy right here is 1 down, H and K, respectively right there. So, I put the standard function on here, but this function goes 1 right and 1 down. I now have a new point. I have 1, -1, which I'm going to plot in the middle. 1, -1. And then I'm just going to plug in some points. So I'm going to plug in 0. I'm going to plug in 2. I'm going to plug in -1. I'm just taking that new place where we originated our graph, right? That new inflection point, and I'm moving it around. If I plug in 0, well, we can plug in 0 pretty quickly in our head. F of 0 equals 2 times 0 minus 1 cubed minus 1. Well, if we did this, -1 cubed is -1, right? 2 times -1 is -2 minus 1 is -3. So f of 0 is -3. All right. That means the other side is going to be -3 as well, or +3 in this case, because it's going in opposite directions. But we can plug that in. Let's do it. F of 2 equals 2 minus 1 cubed minus 1. Well, that's 1 cubed times 2, which is going to be 2. Minus 1 is 1. Oh, let's change this. It won't be -3 because we shifted 1 down. So now we have a 1. Let's go ahead and plot that and see what it looks like. We have 0, -3, and 1, 2. So I want to talk about that real quick and what we've done in the past. If you notice, that's 1 right and 1 down. There's 1 right and 1 down. And this would normally be our vertical stretch. We've said in the past that vertical stretch for these graphs, the first time I move right or left is the change. And if you notice, the first time I moved right, I did go up 2, just like this. And the first time I moved left, I went down 2. All right, so that vertical stretch seems to have the same effect on this graph as it has on the other graph that we've been doing. Let's go ahead and plug in -1. F of -1 equals 2 times -1 minus 1 cubed minus 1. 2 times, well, that's -2 cubed, -8, minus 1, which gives me negative 17. Not going to fit on our graph. Let's do 3. F of 3 equals 2 times 3 minus 1 cubed minus 1. Well, this would be 2 cubed times 2 minus 1, which is 15. So that one's going to give us a 15. Also not going to fit on our graph. And these cubic functions, they get really big really fast. So you'll probably only find one, especially if there's a vertical stretch involved. You're probably only going to find like 1 or 2 points other than the origin that fits on the graph. All right, let's look at this guy. If we just look at this guy, we're going to do the same thing. We're going to plot points. We're going to say, hey, that's 3 left and 4 up. Let's do that. 3 left, 1, 2, 3, and 4 up. We have a point right here. I'm going to put that here. 3 left is negative 3, 4 up. And I'm going to plot a couple points. This would be a horizontal shrink right here. All right, so I'm going to look at that point, and I'm going to try to plug something in that if I was going to horizontally shrink one would make a little bit of sense. So I'm actually going to plug in, I'm still going to go 1 left. We'll go negative 2. Ooh, and 1 right. I'm going to go a little bit different than that. I'm going to go all the way to negative 1. I'm going to tell you why I chose this point. When I plug in negative 1, that's going to give me something kind of easy to plug in. I take that back. Let's go over and we'll plug in negative 2 so it doesn't get too big too fast. And we'll plug in negative 4. So here we go. F of negative 2 equals, we got 2 times negative 2 plus 3 cubed plus 4, which is 2 times 1 cubed plus 4, which is, what do we got? 2 times 1 cubed is 8 plus 4, which gives us 12. So negative 2 gives us a 12 output. Let's go ahead and put that on here, right here. And we will do f of negative 4. It's going to give us 2 times negative 4 plus 3 cubed plus 1. It's going to be 2 times negative 1 cubed plus 1. It's going to be negative 8 plus 1. So f of negative 4 is going to give us negative 7. Right there. Let's go down and plot that. This scale goes by 2's right here, just because of the nature of these graphs. They get really big really fast. But there's negative 7, and right here. We're going to go ahead and plot that, just like that. And something that kind of gives a little swirl when it goes up. Alright. So, if you can plug in your h and k value as the center of the graph and just plot a couple points around, it should be relatively easy to graph. This is a pretty good way of graphing cubics. Just use your h and k to get your origin, alright? And then let's mark that as origin, so when I say that, you know what we're talking about. And then go 1 up and 1 down and plot around it like that. Let's go ahead and put negative 1. We'll just do this one mentally real quick so we have our rest of our points. We should put all the points if we're on a graph like this. So negative 1 plus 3 is 2. 2 times 2 is 4. 4 cubed is 64 plus 4 is 68. Now I see how quick these graphs move up in the y values. Same thing here, negative 5. Negative 5 plus 3 is negative 2 times 2 negative 4. Cubed is negative 64 plus 4 is negative 60. Obviously those points aren't going to fit on the graph, but they're there. So we're going to give you one more to do right here. And you try this one. Take special note of that negative a. That's going to have an effect on this graph. And come back with that graph. See you soon.